One of the fundamental guidelines of the universe is that nothing is amazing. Flawlessness just doesn't exist without defect. Neither you nor I would exist. Stephen Selling, a logical virtuoso, changed how we might interpret the universe through his significant contributions to cosmology. In spite of fighting odds, his work and perseverance continue to inspire and shape logical investigation. Hawking's notable discoveries, especially his work on black holes, pushed the limits of information and tested laid-out hypotheses. Stephen Hawking's black hole theory has been debated by researchers for a long time, but we may finally have proof that it exists thanks to the James Webb Space Telescope, JWST. Known as one of humanity's most advanced galactic instruments, the Webb telescope, through its unmatched capabilities, has enabled the discovery of a wide variety of black holes. These range from faint, distant ones to a few that are incredibly bright and lie even farther away. This data is about to alter our understanding of these confounding celestial bodies. Join us as we dive deep into how the James Webb Space Telescope could change everything we know about black holes. Black holes can often be misunderstood or confused with something evil. What are they? Well, they're curiously captivating objects in space, spots where matter has been crunched down into a very reduced region. If Earth were theoretically squashed into a black hole, it would be under an inch across, yet the object would still be very massive, containing the sum of our planet's mass. The result, a spot with a gravitational force so intense that even light can't escape. This makes black holes seem like all-powerful, unnerving objects with a voracious appetite for stars and planets. In the public mind, black holes are often envisioned as massive, infinite vacuum cleaners that suck up everything in their path. This is a vivid but inaccurate idea. A black hole isn't and doesn't make a vacuum. Quite the opposite, it attracts through the effect of gravity. Because its mass is so immense, it follows that we shouldn't fear it. If the sun were to be replaced by a black hole of the same mass, our world would be a lot colder and darker, but the planets would continue to orbit undisturbed, because the mass of the black hole would be equivalent to that of the sun. The existence of black holes originates from the theory of general relativity, published by Albert Einstein in 1915, and the subsequent work of Robert Oppenheimer, Karl Schwarzschild, Subramanian Chandrasekhar, and others. Space and time form a fabric that is curved by mass, like a trampoline. A black hole is a ball so heavy that it has at its center a singularity, a region so dense that it collapses the infinite trampoline. Any object we place near it will tend to fall toward the ball, so the gravitational effect of the black hole is felt in its surroundings. Astrophysicists have been able to identify numerous black holes by finding vast objects orbiting what seems to be an empty space. This gravitational pull reveals the presence of something otherwise invisible. These black holes are often called stellar black holes. They form after the death of a star, whose internal gas pressure pushing outwards can no longer balance the immense gravitational force, causing its remaining matter to collapse into a black hole. These black holes can be several times the mass of the Sun, though they are small compared to those that can accumulate thousands of solar masses, those that sit at the centers of many galaxies. At the other extreme, there are black holes even smaller than stellar ones, microscopic black holes formed in the early universe. No matter their size, they are all surrounded by an invisible boundary called the event horizon, the point of no return, beyond which nothing can escape, not even light. Around that horizon, masses of dust and gas are accelerated by the tremendous influx of gravity, causing them to heat up and glow, emitting radiation. Sometimes, this forms an accretion disk, which allows us to observe the shadow cast by the black hole itself on the radiant ring. Thanks to this effect, the Event Horizon Telescope, a global collaboration of ground-based radio telescopes, succeeded on April 10, 2019, in providing humanity with the first-ever image of a black hole located at the center of the galaxy M87. In 1974, a study by Selling, published in Nature, shook the scientific world by suggesting that black holes were not as dark as previously thought, nor did they grow infinitely, as physicists, including himself, had previously believed. His brilliance lay in uniting two traditionally opposing worlds, general relativity, the Einsteinian gravity used to explain the formation and evolution of black holes, and quantum mechanics, which describes the nature of the subatomic world. In his earlier papers, Stephen Selling demonstrated how relativity led to the formation of a black hole. But at that point, it was necessary to delve into quantum mechanics to explain what happens at the black hole's core. As physicist Ethan Siegel explained, quantum theory suggests the constant creation of virtual particle-antiparticle pairs that immediately destroy each other. However, if this occurs right at the event horizon of a black hole, it could result in the negatively charged antiparticle falling inwards, taking energy from the black hole, while its positively charged counterpart escapes into space with identical positive energy. Ultimately, this would lead to the complete disappearance of the black hole, with no energy or information remaining. However, as Selling pointed out in the study, for a solar mass black hole, this process would take far longer than the age of the universe. For much smaller black holes, this process would be faster, culminating in a final explosion equivalent to 1 megaton hydrogen bombs. Hawking's demonstration that black holes can emit radiation is his most significant contribution, according to physicist Melda at Princeton's Institute for Advanced Study. However, at the time, this Hawking radiation created a real split between relativistic and quantum physicists, as the latter now faced a difficult problem. If, according to quantum mechanics, the information related to particles is never destroyed, yet Hawking radiation suggests that energy can escape from a black hole, how could a black hole ultimately vanish without taking this information out of existence? Hawking radiation is widely accepted in current physics, though it is extremely difficult to measure and, thus, confirm. Astonishingly, it is emitted in greater amounts by smaller, invisible black holes. Meanwhile, larger ones, those that astrophysicists can study directly, emit so little that it's indistinguishable from the vast background radiation. In any case, a similar phenomenon has been reproduced in the laboratory. Scientists at the Technion Institute of Technology in Israel have created analogs of small black holes that operate with sound rather than light. They have managed to demonstrate something similar to Hawking radiation. These experiments have confirmed two of the physicists' predictions, that the radiation is spontaneously generated from empty space and that it remains constant in intensity over time. However, as far as Hawking's work is concerned, the so-called information paradox has remained the most important of the questions it raised. This conundrum has kept physicists busy for the last 50 years. Selling himself, who until his demise looked indefatigably for a hypothesis proficient of binding together broad relativity and quantum mechanics, as such a quantum hypothesis of gravity that describes what happens inside black holes, the popular physicist's final words proposed a solution for data recovery in the 1970s. John Wheeler, who promoted the term black hole, and Jacob Bekenstein asserted that black holes have no hair in the sense that the only properties a black hole might have were its mass, its electric charge, and its angular energy. In this manner, if one observed a black hole, you could not perceive anything about the way things were shaped since any remaining data is lost inside it. The event horizon is, so to speak, an exposed limit, shorn of all data. However, in 2018, Pedling, Perry, and their teammates found a theoretical method for suggesting that black holes can have soft hair. In the event of an endless assortment of additional properties that a black hole can have, states Perry, this allegorical hair suggests ways in which black holes might monitor data at their surfaces so that this data is eventually recovered. However, Perry warns that while these ideas advance a potential solution to the data paradox, they are not the final word. Recently, different models, in addition to soft hair, have emerged, and there have been exciting developments about recovering data from black holes. According to Tom Banks, a Rutgers University physicist who has had scientific discussions with Pedling, England's contributions have been the most significant work advancing our understanding, although still very limited, of the connection between quantum mechanics and general relativity. This is a road that has been traveled for 50 years, and much still needs to be done. Progress is good, but the timescale for solving these deepest of all issues is long. Andrew Stringer, co-author of the soft hair study at Harvard University, says, "We have been trying to understand black holes for decades. I hope we can wrap it up in another 50. This was in response to the expectations of established researchers. A new discovery from the James Webb Space Telescope, one of humanity's most advanced galactic devices, has left scientists astounded, shedding light on the mysterious nature of black holes. Previously, the existence of black holes in the universe had always been an area of broad study, but JWST discoveries have surpassed astronomers' most out-of-this-world fantasies. The JWST, through its unrivaled abilities, has enabled the discovery of a wide assortment of black holes, ranging from faint, distant ones to a few that are incredibly bright and lie even farther away. This data is going to change our perception and understanding of these cryptic celestial bodies. Many of the newfound black holes lie at redshifts somewhere in the range of 4 and 6, relating to a universe aged around 1 to 1.5 billion years. The JWST's detailed observations have revealed some of the most distant black holes ever recognized. One confirmed discovery lies at the center of a well-studied galaxy, GNZ11, displaying a redshift of 10.6. This suggests that the seeds for black holes had already begun to form supermassive objects early on, about 400 million years after the Big Bang. In fact, the presence of cosmic titans, which have masses millions and even billions of times that of the Sun, doesn't present a problem when supermassive black holes are found in the nearby universe. However, truly massive black holes become a problem when they are found in the early universe, already possessing masses comparable to billions of suns. This is because there must be some mechanism that allows supermassive black holes to rapidly accumulate mass and grow to such enormous sizes. But all the current models for this growth suggest that the process occurs too slowly for such objects to exist so soon after the Big Bang. Royal Society Universe Research Fellow at Maynooth University, John Rand, describes the problem with a somewhat disturbing analogy. It's like seeing a family walking down the road, and they had 2 6-foot teenagers, but they also have with them a 6-foot-tall child. That's a bit of a problem. How did the child get so tall? And it's no different for very large black holes in the universe. How did they get so big, so quickly? This issue is further complicated when the James Webb Space Telescope found the most distant and earliest truly massive black hole, located at the center of the galaxy SPT 31158. This black hole has a mass of 9 million times that of the Sun, which makes it relatively small for a supermassive black hole. Yet, even at this size, its existence just 570 million years after the Big Bang challenges theories of black hole formation. This 9 million solar mass black hole was not alone. The same observation effort that uncovered this massive black hole also revealed 2 other supermassive black holes that existed 1 billion and 1.1 billion years after the Big Bang. According to Professor Shantanu Nasu from the University of Western Ontario, with each new discovery, the constraints on our current models become stronger. We were concerned when supermassive black holes were seen 800 million years after the Big Bang. Now it only increases the challenge massively. This suggests that supermassive black holes are common in the early universe, not just some cosmic anomaly, thereby putting pressure on the search for a mechanism to explain how they got there. Current theories on early-stage black holes speculate that they may be the remnants left over after the Big Bang. The 3 main categories of black holes are stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes form when the most massive stars run out of fuel for nuclear fusion and can no longer support themselves against their own gravity. As the outer layers of these stars are blown away in massive supernova explosions, the cores collapse to create stellar mass black holes, regions of space with a point of infinite density at their center and an outer limit, the event horizon, where gravity is so intense that not even light can escape. Supermassive black holes must form through a different process, as it is impossible for a single star to be large enough to have the mass required to shed mass as it develops through processes like these. A cosmic explosion that goes with the gravitational breakdown of the star yet still abandons a center sufficiently gigantic to turn into a very huge black hole. For numerous years, space experts have accepted that very large black holes could begin their lives as seed black holes that are much smaller, growing by first benefiting from material and then combining with other black holes when the galaxies they dwell in impact. This also gives these sprouting supermassive black holes gas and dust to feed on. the growth of supermassive black hole seeds could happen when these vast seeds find themselves surrounded by large amounts of matter and insatiably devour this material to develop quickly into very large black holes. This process, however, should be hindered by something many refer to as the limit. The glow and brilliance of a feeding black hole are proportional to the rate at which they are gathering mass. The quicker a black hole consumes matter, the faster it grows, and the faster it grows, the more electromagnetic radiation is impacted out by its environment. However, if the electromagnetic radiation discharged from around a black hole, as jets, is intense enough, it can drive material away. This means that the faster a black hole eats, the more likely it is to have its food hindered and driven away, thereby stopping that growth. This limit suggests that it should take black holes billions of years to accumulate enough matter to reach very massive black hole status. Rand is part of a group of specialists that explored something many refer to as super Eddington growth, which could account for the rapid development of very large black holes in the early universe. This wouldn't be made sense of as anything especially exceptional, just a faster version of ordinary black hole feeding. This would lead to fast episodes of feeding with material being driven away by jets, stopping the feeding and thereby cutting off the jets. This then allows the material to fall back to the black hole, triggering another episode of excited devouring. Reagan and partners found this explanation inadmissible. However, he said, if you average this feeding cycle over time, it's not quite the Eddington rate. It may be acceptable for a few cycles, but overall, over the long run, it's not great because it just can't and doesn't go on continuously. So, we didn't observe that this was an extraordinary mechanism to truly make sense of very massive black hole development, he expressed. Another possibility that could explain the rapid growth of very large black holes is the idea that the seed black hole from which they develop is already large in size. Massive black hole seeds would still need to get into these dense conditions, but at least they would have an early advantage over smaller seeds. Going back to the 6-foot newborn relationship, Reagan explains that the development of this child is much harder to explain if it was born with the length of a typical baby. However, if this child was born already 3 feet long, its growth into a 6-foot-tall toddler is not so difficult to explain. The problem with studying this is, unlike babies, black holes lack attributes beyond their mass, angular momentum, spin, and electric charge. Researchers call this the no-hair hypothesis. It means that black holes are deceptively simple and don't carry information about their histories or evolution. Basu added that observing the feeding process that is building up black holes in the early universe hasn't been possible since it has been happening so far away from us. However, detecting very massive black hole feeding might be possible in the future. The speculative supermassive stars in the early universe would be incredibly luminous, perhaps 10 billion times as bright as our Sun. It's possible that the JWST or other upcoming space telescopes could detect such objects, if they exist, as late as a few 100 million years after the Big Bang. Basu reported that despite these challenges, Reagan is confident that by exploring black holes in the early universe and by potentially finding heavy seeds, researchers will soon be able to build a very large black hole growth picture. Specifically, he pointed to the launch of the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector, which will assist researchers in better understanding the demographics of black holes in the early universe. We've made a huge amount of progress in the last 10 years, enormous, and we will continue to make enormous advancements over the next 10 years as well. Extrapolating out from these observations will give us a very good handle on the number of mergers occurring in the distant universe, including black holes in the very mass range we need, with masses around multiple times that of the Sun. I think it is entirely likely we will have solved this issue in the next 5 to 10 years, he said.